in the problem of oscillations, till now we have discussed free oscillations with 1 degree of freedom. And you have seen in case of the free oscillation, the amplitude of oscillation remains constant, because in that case there is no resistive force, no damping force, and the energy of the oscillator remains conserved or constant, and so that its amplitude also remains constant. And so once a free oscillation is caused, it takes place or it continues for infinite time. But in actual practice, the examples of free oscillations are rare, because whenever we perform experiment in practice, definitely the oscillator oscillates in some medium, and the medium offers some resistive force on the oscillator. And due to that resistive force, or you can also say damping force, the energy of the oscillator does not remain constant, but this energy decreases gradually, continuously with time. And as the energy of the oscillator decreases continuously with time, so that the amplitude of oscillation does not remain constant. Actually, such oscillations are known as damped harmonic oscillations. So now in present video, our aim is to deal with the problem of the damped simple harmonic oscillations with 1 degree of freedom. Here this restriction of 1 degree of freedom is present in this problem too, as you have learned the free oscillation in case of 1 degree of freedom. So in this case our oscillator will have only 1 degree of freedom. When you say 1 degree of freedom, that means the displacement of the oscillator depends only one parameter, that is time, not more than one parameter. So it is called oscillation with 1 degree of freedom. Okay. So now let us consider there is an oscillator, and that oscillator is oscillating in a medium like air, or you can say like any other medium like water, and this O is the equilibrium position, and the oscillator is oscillating about this equilibrium position O. So in this case, as I have told you, that our oscillator experiences a resistive force along with the restoring force, because you know oscillation takes place only when there is some restoring force acting on the oscillator. So in this case too, the restoring force will present, which will provide oscillation to the oscillator. But apart from that restoring force, our oscillator also experiences some retarding force, and that retarding force or damping force or resistive force is due to the medium, and that retarding force actually decreases the energy of the oscillator continuously, as I have told you. And due to the decrease of energy, the amplitude of oscillation decreases gradually and continuously until it becomes zero. It means finally the amplitude of oscillation becomes zero. We will see later on that actually the amplitude of oscillation varies with time and it decreases with time exponentially in accordance with this relation. We will derive this relation in the final part of our lecture, but I have written it here directly. If you consider that this A is the amplitude of our oscillator at any time t, then A is given by this relation. This is A naught e to the power minus bt. Actually here this A naught is the amplitude of the oscillator at t equal to 0. It means initially its amplitude is A naught, but B is a positive constant, which is called actually damping constant, and t is time. So you can see this amplitude decreases with time exponentially. I have shown this variation of amplitude in this figure. Here at t equal to 0, the amplitude A naught you can see, and as the time increases, the amplitude decreases exponentially. And according to this relation, when t will tend to infinity, then amplitude will become 0. This will become 0. So finally, the oscillator stops oscillation in this case. Okay. Actually, this decrease or decay of amplitude with time is called damping. What do you mean by damping? Damping is the decay or decrease of amplitude with time. And this type of oscillations are known as damped harmonic oscillations. And as I have told you that in this case too, like free oscillation, we are going to discuss the damped harmonic oscillation with 1 degree of freedom. It means in this case, the displacement x of our oscillator will be only a function of variable t, only one variable t, and so it is called oscillation with 1 degree of freedom. So I think you have understand what is this damped harmonic oscillation. Okay. Now actually this lecture on damped harmonic oscillation, we will divide it in two parts, because if I will wish to finish the whole concept in one lecture, that will be very lengthy and not you will enjoy it. So for your convenience, I will divide this lecture in two parts. In this first part of the lecture on damped harmonic oscillation, we will actually find the differential equation of motion of this oscillation, of this oscillator, and then we will try to solve it. In fact, we will obtain the general solution of the equation of motion of the damped harmonic oscillator. And in the second part of the lecture, we will see some of the specific situations, that is how much damping is present. We will consider three cases. In first case, we will consider high damping or over damping, you can say, or you can say deadbeat damping. And in the second case, we will consider critical damping. And finally, in third case, we will assume low damping. And you will see that only in case of low damping, oscillation takes place. In fact, in first two cases, that is in case of the over damping and the critical damping, there is no oscillation. Oscillation takes place only in case of low damping. And that will be the subject matter of the second part of this video. So this is damped oscillation part first. Okay, this is your part first. So now let us try to find the equation of motion. Okay, when you say equation of motion, that means you have to apply Newton's second law of motion, and applying Newton's second law of motion, we can obtain the equation of motion. And for this, let us consider an oscillator. Here, oscillator may be a mechanical oscillator, it may be an electrical oscillator. Okay, but in this example, I am considering here a mechanical oscillator. Let us consider there is a particle or any body of mass m, and it is oscillating about its equilibrium position O. O is the equilibrium position. It means net force on this oscillator when it is at O is 0. And during this oscillation, at any time t, our oscillator is at the point P when its displacement is x, as I have shown in this figure. Okay. Now, as you have seen in the case of free oscillation, our oscillator experiences only one force, that is called restoring force. But as here, our oscillator is oscillating in a retarding medium, so along with the restoring force, our oscillator will also experience a retarding force due to the medium. So taking under account these two forces, we can easily obtain its equation of motion. So let us consider at any time t, the displacement of the oscillator is x, and so its velocity at time t will be dx by dt, which I have denoted by the symbol v. Okay, and as I have told you, there are two forces acting on our oscillator. The first one is called restoring force, and I have denoted this restoring force by the symbol Fs. Okay. You know, this restoring force is directly proportional to the displacement of the oscillator, but it always opposes to the displacement. It means this restoring force is directed in the direction in which this displacement x will decrease. It means the nature of restoring force is what? Its nature is to decrease x, and so mathematically you say that Fs is proportional to minus x. Actually, this minus sign here only implies that this restoring force always tends to decrease x. It acts in the direction in which x will decrease, and that's why we put here minus sign. Okay. And when you will remove the proportionality, then you have to put here some constant. So I have put it here constant k. So Fs, which represents the restoring force, is given by minus k times x. Here x, you know, this is called force constant, or it is also called a stiffness constant or a spring constant. Okay. And as I have told you that this negative sign implies that the direction of restoring force is opposite to that of the displacement. Okay. And that's why we put here minus sign. Okay. So this is the restoring force acting on our oscillator when its displacement is x. Now, when the oscillator oscillates, you have also seen that in this case there will be a resistive force or retarding force acting on the oscillator. So the second force acting on our oscillator is called resistive force or retarding force, and I have denoted it by the symbol Fr. You know, a resistive force is nothing. This is simply force of friction, and force of friction always opposes the relative motion. So this force will have a tendency to oppose the relative velocity of the oscillator. So when the oscillator moves away from the equilibrium position, let us say in this direction, velocity is in this direction, then this force will act just opposite to it. That is, if the velocity is in rightward direction, this force will be directed to the leftward direction. But when our oscillator is moving in leftward direction, then this force will act in rightward direction. So Fr always opposes the relative velocity of the oscillator. And as you know, velocity at any time t has been defined by dx by dt. So this force is directly proportional to the velocity of the oscillator with respect to the medium. This is actually relative velocity. This is velocity of the oscillator with respect to the medium. Okay. And since this retarding force opposes this velocity, it is directed in opposite direction of the velocity. So we write Fr is proportional to minus dx by dt. Okay. And here you can write Fr equal to minus r times dx by dt. Here r is the proportionality constant, which is called damping constant or resistive constant. And the significance of minus sign, I have already told you that this minus sign shows that Fr is always in opposite direction of the velocity of the oscillator. So these are the two forces acting on our oscillator at any time t. And so you can easily find what will be the resultant force or total force or net force acting on the oscillator at time t. If you denote the resultant force by the symbol this capital F, what will be this capital F? This will be simply the sum of Fr and Fs. And so you can say that F is equal to minus r times dx by dt minus kx. Okay, minus kx. But according to Newton's second law of motion, the resultant force is given by what? Second law says that resultant force acting on a particle is simply equal to the product of mass of the particle and the acceleration of the particle. As at any time t, the velocity of the particle is v, so its acceleration will be dv by dt. Okay, and you know that v is defined as dx by dt. V is equal to dx by dt. So acceleration is d dt dx by dt, which is written as d2x dt square. It means the second order derivative of displacement x will give acceleration. So instead of f in accordance with second law of motion, you can write m times d2x by dt square, and that will be equal to minus r times dx by dt minus kx. Okay. Now let us divide the RHS by this m, or you can also say that we divide both sides of this equation by m. Then bring the terms, these two terms in RHS in LHS. Then what will be your result? You can see after dividing by m, we will get d2x by dt square plus r over m dx by dt plus k over m into x equal to 0. Okay. And this equation may be written like this. This is d2x by dt square plus 2b dx by dt plus omega naught square x equal to 0. Actually here I have made two substitutions. You can easily mark it that this 2b has been written at the place of r by m, and this omega naught square has been written at the place of k over m. So you can say that omega naught is equal to a square root of k over m. Actually, this b is called damping coefficient. This depends on the nature of the medium. Okay, and it is called resistive constant or damping coefficient. Actually, I have written the constant in the form 2b, not simply b. You can write only b. But this 2 factor has been taken in this constant for convenience. You will say later on, we will have a quadratic equation. And if you write this constant like 2b instead of b, then you will see that the roots of that quadratic equation will be obtained in simpler form. So for simplicity, the constant has been expressed by multiplying 2. It is not any new thing. You can say if our constant is 10, I am not writing 10, but I am writing 2 into 5. Fact is same, but this 2 factor will play a very nice role for simplifying the equation. Okay. So, and this omega naught is what? This is called natural frequency of our oscillator. Okay. Omega naught is known as natural frequency. Okay. And you have seen this expression while discussing the free oscillation or simple harmonic motion in my previous lectures. Okay. So this equation which we have obtained here, you can see this equation d2x by dt square plus 2b times dx by dt plus omega naught square x equal to 0. You can see this is a differential equation of second order or and with constant coefficient. Okay. Actually, this differential equation of second order is known as the differential equation of damped harmonic oscillator or damped harmonic oscillation with 1 degree of freedom. Okay. Here there is only one independent variable, that is t, on which our dependent variable x depends, and so it is the equation of motion of a damped harmonic oscillator with 1 degree of freedom. Okay. So in this way, very easily you have obtained a differential equation of damped harmonic oscillator. Now our problem is to solve this equation. How we can solve this differential equation? This is our purpose now. Okay. And as I have told you, in this lecture we will obtain its general solution, and the discussion of that general solution will give some very interesting results which will be discussed in the second part of the lecture. So now let us try to solve this equation. Actually, you can see if this second term was not present, then this equation will be simply the equation of motion of a free oscillator. But due to this damping term, this is not equation of a free oscillator. Even now, if you consider that B is equal to 0, it means there is no damping, then this equation will become d2x by dt square plus omega naught square x equal to 0, and you know that equation is simply the equation of free oscillator. Okay, but due to the presence of this second term, this equation is the equation of motion of the damped harmonic oscillator. Actually, this second order differential equation will be solved by considering a trial solution. So how we can solve this equation? Let us see the steps. We consider actually a trial solution, and that trial solution is given by x is equal to c times e to the power alpha t. You know, the solution of this equation will be x, and x we have defined like this, c times e to the power alpha t. Actually here, this c and alpha both are arbitrary constant. These constants had been assumed by the observer. So these are called arbitrary constants. Okay. Now we have assumed this, and considering this trial solution, as you can see in our equation, there are two remaining terms which contains the second order derivative of x and first order derivative of x. So let us find first of all these two derivatives, and then we will substitute those values in that equation of motion, and we will get the solution. So x is equal to c times e to the power alpha t, and you can easily say then what will be dx by dt. Okay, you know c is a constant, so it will remain at age, and the derivative of e to the power alpha t with respect to t will be what? That will be alpha times e to the power alpha t. So dx by dt is finally alpha times c e to the power alpha t. But you can see equation 1, this c times e to the power alpha t, this is x. So instead of this, I have written here x. So dx by dt is simply equal to alpha times x. Okay. Now again differentiate this dx by dt. So when you will differentiate dx by dt again with respect to t, you will get d2x by dt square. And what will be that? That will be again derivative of e to the power alpha t will be alpha times e to the power alpha t. So your result will be alpha square c e to the power alpha t. And again I have written x instead of this c times e to the power alpha t. So the second order derivative of x, that is d2x by dt square, we get this is alpha square times x. Now let us substitute the value of this dx by dt and d2x by dt in this equation of motion defined in A. Okay, at the place of d2x by dt square and dx by dt. You can see after substituting this, we will get alpha square x plus 2b alpha x plus omega naught square x equal to 0. As you can see, since x is a common factor, so this result can be written as x times alpha square plus 2 beta alpha plus omega naught square is equal to 0. Now you know this x is the displacement of our oscillator, and since the oscillator is oscillating about its equilibrium position, when the oscillator is at equilibrium position, then x is 0. But whenever it is away from the equilibrium position, x is not 0. So this x is varying with time. It is not 0 at all time t. It can be 0 only when the oscillator will be at its equilibrium position. So this x is not 0 at all time t, but in RHS our result is 0. So definitely the factor inside this square bracket, that is alpha square plus 2b alpha plus omega naught square, that must be equal to 0. And you can see In this way, we get the result alpha square plus 2b alpha plus omega naught square equal to 0. In this equation, you can see that 2b and omega naught square are constants. And so, this is a quadratic equation in alpha. Quadratic equation in alpha. This is just in the form of ax square plus bx plus c equal to 0. Okay. At the place of a, there is 1 here, and instead of x, there is alpha. So this is a quadratic equation in alpha, and you know any quadratic equation has two roots. It means this alpha will have two values which are called roots of this quadratic equation. And according to the standard formula of the roots of a quadratic equation, you can write what will be these roots. Alpha will be equal to, you know, this is minus 2b plus minus root over 2b square, it means 4b square, minus 4ac. A is 1 and c is omega naught square. So this is minus 4 omega naught square, and divided by 2a, but a is 1. So you can say that alpha is equal to minus 2b plus minus a square root of 4b square minus 4 omega naught square over 2. You can see that this 4 inside the square root can be taken as a common factor. And when you will write it outside of the square root, that will be 2. So in numerator, 2 will be a common factor. And since in denominator there is also 2, so these two will cancel out. And your result will be minus b plus minus a square root of 4b square minus a square root of b square minus omega naught square. Now taking this plus and minus sign separately, you will get the two roots. So when we take this plus sign, then our root is alpha 1, and that alpha 1 will be what? That will be minus b plus root over b square minus omega naught square. Now let us take the minus sign, and taking minus sign, you will get the second root of this equation, which is alpha 2, and that alpha 2 will be equal to minus b minus root over b square minus omega naught square. Okay. So in this way, we have obtained the two roots of that quadratic equation. Now, the general solution of this equation A, which you have written here as in the form of a trial solution, now you can write it. Actually, you can see this is a differential equation of second order, and you know whenever a differential equation of second order is solved, there will be two integration constant. Actually, in this case, we will have to integrate 2 times, and during 2 integration, we will have 2 integration constants. So the general solution of that very equation is written as x of t equal to an arbitrary constant a e to the power alpha 1 t plus b times e to the power alpha 2 t. Okay. Now let us substitute the values of alpha 1 and alpha 2 here. So x of t, this will be equal to a times e to the power alpha 1 t. But you can see alpha 1 is this much. This is minus b plus root over b square minus omega naught square times t. So t has been written it here. And plus b e to the power alpha 2t, and alpha 2 is this much. So b times e to the power minus b minus root over b square minus omega naught square times t. Okay. Now you can see this exponential factor can be written like this. This is e to the power minus bt times e to the power root over b square minus omega naught square into t. And similarly, in the second term, this e to the power minus bt will be a common factor. So e to the power minus bt can be taken as a common factor, and you can write that x of t is equal to this much. This is e to the power minus bt times a times e to the power square root of b square minus omega naught square times t, and plus b times e to the power minus square root of b square minus omega naught square into t. Now for convenience, we take a square root of b square minus omega naught square is equal to p. We have considered it for simplicity. And so at the place of this root over b square minus omega naught square, now write p. And so you can write x of t is equal to e to the power minus bt times a times e to the power pt plus b times e to the power minus pt. Okay. And as I have told you earlier that these a and b are arbitrary constants, or actually these are integration constant. And you know, in actual physical problem, you have to find the actual values of the arbitrary constants. And what is the technique of finding the values of these integration constants? Integration constants are always evaluated by using the proper boundary conditions. Here in our equation, there are two arbitrary constants a and b. And for finding or evaluating the two arbitrary constants, at least we have two boundary conditions. At least two boundary conditions. Okay. So considering the two boundary conditions, we can evaluate the values of constants a and b. So for evaluating these these arbitrary constants or integration constant, let us consider the two boundary conditions. You can see this figure. I have considered that at time t equal to 0, our particle is located at this point P, which is at a distance x naught from the equilibrium position. So you can say when t is 0, then x is equal to x naught. And at this moment, the particle is at rest. Particle is at rest. Actually, the particle has been released from this point, so it starts moving under the restoring force with 0 velocity. So at t equal to 0, you can also say that v equal to dx by dt, and that is also 0. So we will use these two boundary conditions to evaluate the value of a and b. So what is your first boundary condition? This is x is equal to x naught when t is equal to 0. And what is your second boundary condition? It is dx by dt is 0 when t is 0. I have written it here for your convenience. You can see the first boundary condition is x is equal to x naught at t equal to 0, and v is equal to 0 at t equal to 0. Applying these two boundary conditions, you can see we can easily evaluate the arbitrary constants a and b. Okay. Now, first of all, apply this first boundary condition, which reads x equal to x naught at t equal to 0 on this equation b. Okay. So when you will apply the first equation, how you will apply? You have to write t equal to 0 in RHS, and at the place of x, you have to write x naught. So what will be this equation? See here. When you will put t equal to 0, you can see all the exponential term will have power 0. And you know e to the power 0 is 1. So all exponential factors becomes 1. Okay. And x is now x naught. So applying the first boundary condition or that very equation, our result will be x naught equal to e to the power 0 times a times e to the power 0 plus b times e to the power 0. And so you can write x naught equal to a plus b, because you know e to the power 0 is equal to 1. Okay. So our first boundary condition when applied on our resulting equation has provided this result, x naught equal to a plus b. You can see by the use of first boundary condition we have obtained only an equation in which a and b are present. We have not found the value of a and b, but an equation we have obtained which contains a and b. Now if there will be another equation containing a and b, then we can solve those two equations to get the value of a and b. For getting the second equation, we have to apply this second boundary condition. But the second boundary condition has been applied for the velocity of the particle. But this equation b is for the displacement. So before applying the second condition, you have to find the velocity of the oscillator at any time t. And how you can get the value of velocity? You know, velocity is simply the time derivative of this x. So first of all, find the velocity of the oscillator at time t for applying the second condition. Okay. So you can see the velocity of the oscillator at time t, which is defined by dx by dt, will be what? This is your equation. This is your equation. And you can see in RHS there is a product of two functions or two factors. The first factor is e to the power minus bt, and the second factor has been written in this inside this square bracket, which is a times e to the power pt plus b times e to the power minus pt. So applying the rule of differentiation of product of two functions, you can easily differentiate it. When we will differentiate this factor e to the power minus bt, then we will keep this factor inside the square bracket at each, and when we will differentiate this factor inside the square bracket, then we will keep this e to the power minus bt at each. Okay. So let us see the derivative of this x. I have here differentiated e to the power minus bt, which is minus b times e to the power minus bt. And the second factor of inside the square bracket has been kept at each. Okay, you can see. Now, keep this e to the power minus bt at each and differentiate this factor. This factor will be now differentiated. And you know what will be the derivative? This will be p times a e to the power pt minus p times b into e to the power minus pt. Okay, this is a very simple differentiation. Okay, and we can simplify this equation a little bit. You can see v of t will be equal to minus b times e to the power minus bt times this much a e to the power pt plus p e to the power minus pt. And as this p is contained in both terms inside this square bracket, so you can take this as a common factor. So p has been taken as a common factor, and the second term becomes p times e to the power minus bt times a times e to the power pt minus b times e to the power minus bt. So this is velocity of our oscillator at any time t. Now we will apply this second boundary condition, which says v is 0 when t is 0. On this equation 4, we will apply it. So when you will apply the second boundary condition on equation 4, what you will do? We will simply put t equal to 0 in RHS, and in LHS at the place of v, then we will put 0. Okay. Again, you can mark it. When t will be taken 0, all the exponential factor will have power 0, and so that all exponential factor will be now 1. Okay. So what will be our result? You can see this will be simply 0 equal to minus b, because e to the power minus bt, that will be e to the power 0 and 1. and inside this bracket there will be a plus b, because exponential factor is 1 now, and plus p and times a minus b. Actually this result I have written it here. You can see when I have applied this second condition on equation 4, our result is 0 equal to minus b times a plus b plus p times a minus b. Okay, and so you can write this p times a minus b equal to b times a plus b. But see your equation 3. A plus b we have just obtained, this is equal to x naught. So in this equation 2, replace this a plus b by x naught. Okay, so at the place of a plus b I have written here x naught. So our result is what? This is p times a minus b equal to bx naught. Here I have written that here the use of equation 3 has been made. Okay, and that's why you can say that a minus b is equal to b over p times x naught. Now see, now we have two equations. One equation is here 5, which contains a and b, and there is equation 3 which also contains a and b. And solving now these two equations 3 and 5, whose solution is very easy, we can obtain the value of arbitrary constant a and b. If your aim is to find a, what you will do? We will simply add these two equations. Equation 3 and 5 will be added. And you can see when we will add these two, this b will be cancelled out, because in equation 3 it is plus and in equation 5 it is minus, so they will cancel out, and a plus a will be 2a. A plus a will be 2a. And here there is x naught, and in equation 5 there is b by p x naught. So x naught will be a common factor, and the remaining terms will be 1 plus b by p. And so if you want to find a, you will have to divide this x naught by 2. So I have written it here. You can see that a will be equal to x naught over 2 times 1 plus b by p. So in this way we have obtained the value of the arbitrary constant a. Okay. Now for getting the value of second constant b, we will simply subtract this equation 5 from 3. And when you will subtract, what will be your result? You can see a plus b minus a minus b. What will be this? Actually here a and a will cancel out and b will be added, so this will be 2b. And in RHS there will be x naught common 1 minus b by p. And so when you want to find this b will be now equal to x naught by 2 times this much. So I have written, you can see b is equal to x naught over 2 times 1 minus b by p. Okay. So these are the values of the arbitrary constants a and b. So now let us substitute these two values in our general solution, which we have obtained here in equation b. At the place of a and b, we will substitute those values which we have just obtained. Okay. So see this equation. At the place of a, now what we will write? That will be written as x naught by 2 times 1 plus b by p. And at the place of b, now you have to write x naught by 2 times 1 minus b by p. Okay. X naught by 2 will be now again a common factor. That will be a common factor. And our result will be what? X of t equal to e to the power minus bt times, at the place of a, we have to write 1 plus b by p times x naught by 2. And the remaining factor is e to the power pt. You can see the previous equation. And at the place of b, I have written here 1 minus b by p times x naught by 2. And this is the exponential factor e to the power minus pt. And you can take this x naught by 2 as a common factor. So see this equation. This is x naught by 2 times e to the power minus pt. Now 1 plus b by p times e to the power pt plus 1 minus b by p times e to the power minus pt. Now let us multiply by the exponential factor to the terms inside the bracket. So 1 times e to the power pt. This will be e to the power pt. Okay. And in second term 1 times e to the power minus pt. So this is plus e to the power minus pt. Okay. Now in the remaining term in first term will be what? This is b by p times e to the power pt. And here there will be minus b by p times e to the power minus pt. So you can take b by p as a common factor, and the remaining factor will be what? The remaining factor is e to the power pt minus e to the power minus pt. Okay. Now you can take this 2 inside the bracket, and so this result can be written as x at time t, or x of t is equal to x naught times e to the power minus bt times e to the power pt plus e to the power minus pt over 2, and plus b over p times e to the power pt minus e to the power minus pt over 2. Okay. So this is the general solution of the equation of motion of damped harmonic oscillator. You also know that e to the power pt plus e to the power minus pt divided by 2, this is equal to cos hyperbolic pt, and e to the power pt minus e to the power minus pt over 2, this is sin hyperbolic pt. So instead of these two factors, you can also write here cos hyperbolic pt and sin hyperbolic pt. But our discussion in the second lecture will be more easy when we will keep this general solution in the exponential form instead of the hyperbolic functions. So I have not written here cos hyperbolic pt and sin hyperbolic pt. Okay. So this is the last equation, or this is the which we have obtained in this lecture, and this is called actually the general solution of the differential equation of damped harmonic oscillator. Actually, the nature of this solution will depend on the value of p. P you have written, you have seen earlier that this is a square root of b square minus omega naught square. So what is the value of this damping coefficient? That will decide the nature of the motion. That will decide the value of x, how x will vary with t. That will be solely determined by this value of taking this value of b. It means this b is either greater than omega naught or equal to omega naught or less than omega naught. That matters. Okay. So these three cases we will consider in the next part of this lecture, and I hope definitely you have understand the calculations, what is this damped harmonic oscillation, how we can obtain its differential equation of motion, and how we can solve it. Okay. So watch the video seriously, write down these things in your notebook, and definitely then you will get more and more benefit. Okay. Thank you very much.